We're going to start off today talking about this concept of resonance. Again, it's probably something you had in general chemistry. So we're going to kind of review some of the gen chem that's important to us. And then very quickly, we're going to kind of build on that and be much better at resonance than you probably were in general chemistry. So we'll kind of also build in a little bit of Lewis structure building here. And so what we're going to do is we're going to say, let's say, for example, that we have to give the structure for something like NO3. You might think that you could just kind of put the nitrogen in the middle of some oxygens and kind of play around with multiple bonds. And yeah, you probably could do that, but oftentimes you'd end up with the incorrect answer. And so let's actually go through those steps that you learned in Gen Chem. In some, I'm sure you learned it in some capacity. It may not be exactly what I'm doing here. If it works for you, do it. But what I always like to do is I always take the total up my total number of valence electrons, and I make myself a little table here. No! And then I just enter the number of valence electrons that I know that this thing is going to come to the party with. I know a nitrogen has 5, and oxygens all have 6. And then the charge means that there's one additional electron because electrons are negatively charged. So what I'm going to do is kind of a number that I have to make sure I match when I get to my final Lewis structure. I have to make sure that these guys all add up to whatever the heck that number is, 11, 17, 24, 25, that's not right. 7, so that's 18, 24, oh my God. I have a condition known as board brain where I can't do math on the board. I probably can't write my name on the board either. So 24 valence electrons, and I have to show 24 electrons total in my Lewis structure in order for it to be correct. So the first letter or the first element is usually what's in the middle of all the other stuff. So let's just start off by building that. So keep in mind that each one of these single bonds is actually 2 electrons. So what I do is after I've connected together everything is I go and subtract the number that I just used. And assuming my board brain isn't happening, I end up with 18 electrons still left over. And what I do is I just kind of throw a bunch of dots around the outside of this thing. Notice I always work outside to inside. I call that wax on, wax off. You've probably never seen the original Karate Kid. Mr. Miyagi would be proud. So at this point, I've added 6 plus another 6 plus another 6. And what I've done is I've used up all my electrons now. And so, you know, I might think that I'm done. Well, I have to also make sure that I've satisfied octets on everything. And so obviously I need to put some sort of multiple bond in. So I'm just going to arbitrarily pick this guy and put a double bond there. Right? And so this is what's called a valid Lewis structure for this compound. But there's a little bit of a problem. Because it turns out that I also, instead of putting the double bond there, I could have, instead of putting it there, also put it up here. Or I could put it down there, right? That's perfectly valid. So let's write down all of those different examples, and we'll talk a little bit about them. Okay, here are the 3 different answers that are all valid Lewis structures for NO3 minus or nitrate. One of the things that, you know, it looks kind of like I'm just kind of moving the double bond around, and I guess I am, but this is actually a really important concept known as resonance. It turns out that the true picture of NO3 minus is really a perfect mix of all 3 of these things. In other words, if I highlighted, let's say, this bond, which corresponds to that and corresponds to that, It's not like this thing spends part of its time as a single bond and a little bit of its time as a double bond, and then again a little bit of its time as a single bond. It turns out that it's actually showing us that there's something wrong with the bonding theory that we're using right here, and it leads actually to some really complex bonding theories that we'll talk about next week, which I never am excited about because I got to talk about quantum mechanics, which I never have understood. But anyway, this guy is really this like perfect mix of all of these. And these arrows that I'm using right here are called resonance arrows. And these are kind of an attempt, the whole idea of resonance is an attempt to still use what's called covalent bond theory, but not have to worry about using molecular orbital theory. And that is really, really nice. Believe me, you'll know this next week. That we want to try to stay away from molecular orbital theory. And the cool thing about resonance is if you learn a couple of rules, which we're about to learn, it actually is not too bad. It actually is a super great theory with all kinds of predictive capacity. Before we finish here, we should kind of make sure that we calculate formal charges for all these guys. And so if you were to do that, you would end up with this. And so this concept of resonance, right? I think it's probably best understood through a metaphor. And it would be like describing the color green, right? Let's say there's a world where you can't talk about green. Instead, what you have to do is you have to talk about like the fact that green is a mix of blue and yellow. Right? It's not like it's either blue sometimes and then yellow other times. No, it's like a mix of those two things, right? And so resonance is very much like that, where when you see resonance arrows like this, it's trying to tell you that something is kind of a mix. Now here it's an even mix of all three of these different forms because these are all completely equivalent in terms of formal charge and like satisfying octets and everything else. But even that is actually relatively unusual. It turns out that even among resonance forms, things might look a little bit more like one resonance form than another. So in other words, like in our metaphor example of the green, right, it might be more of a blue-green than it is a yellow-green, let's say. So this is kind of usually the typical thing that you do to kind of introduce resonance. If you need a little bit extra help on this, feel free to ask me in office hours. What we're going to do now is we're going to kind of practice some of those Lewis structure drawings with kind of organic-y things that are a little bit more complicated. And what we're going to do is drastically expand this resonance picture here, and we'll start to pick up a couple of the rules that we're going to be using throughout this next couple of terms. Okay, so we've got isothiocyanate, but of course you knew that, NCS minus. So let's go through and we'll total up all the electrons just to make sure that when we start throwing double bonds in, we don't do anything crazy. So we've got nitrogen with 5, carbon with 4, and sulfur with 6, and of course we've got a charge, so we have to have the 1 extra for the charge, and I think when we add all that up, we end up with 16 total electrons. Okay, so anytime you're not 100% sure, as I said, I'd always total up the number of valence electrons there, and now we're just simply going to connect everything together as it is already written. Keeping in mind that every time that we've got a bond, that counts for 2 electrons. So I've just used up 4 of my total just to kind of initially get those guys clung together there. And now I've got 12 electrons left over that I'm going to do the old wax on, wax off trip. Thank you, Mr. Miyagi. And we're going to fill up the outside. And if you don't remember that from Gen Chem, always fill up your electrons on the outside before you move to the inside. That's a really important trick. We're going to stop for a second, and we're going to look at this and say, okay, I obviously need to do something about the fact that carbon isn't happy in the middle there. And so I'm going to take, let's say, 2 electrons from sulfur. and put them there, and 2 electrons from nitrogen and put them there. And I pause and I say, okay, is everybody happy? Woohoo, everybody's happy, everybody's got their octet. But now I have to remember that I had that minus charge there, so there must be a minus charge in there somewhere. And I go through all of my formal charge rules, and I realize, oh wait, my nitrogen is actually the one with the minus charge. And we stop and we say, woohoo, we're all done. No, not really, you're not quite done. Because back at the point where we had carbon in the middle, which was unsatisfied, let's kind of go back to that. I'll leave this on the board, and then we'll go back to what we originally had. And let's say that instead of making this world perfectly symmetric where I put both of those double bonds there, what if I put, let's say, sulfur with a triple bond over here, and then I did that same count of formal charge? Well, it turns out now I've got nitrogen with a 2- formal charge. And again, if you need help calculating that or want to see me do it, I'd be happy to. And you look over here, and this one well, it's probably going to be a plus. It has to be a plus. Let's just do it to make sure real quick. So we had a valence of 6, we had 3 bonds, and we subtract another 2, and in fact, that thing is in fact a positive 1. Okay, so we look at this, and we're not done, by the way, but we look at this and we compare the two, and we recognize that there's a whole bunch more charge here than there is in that one, right? And so one of the rules that we're going to learn is if you're kind of looking at 2 different resonance forms, and one has a whole boatload of formal charge, usually you choose the one that has a more minimized formal charge. So just based on that argument alone, I know already that yes, this picture might look a little bit like this, but it looks a heck of a lot more like that, according to these kind of resonance arguments that we're talking about here. Well, just like we could have put triple bond there, we could have put a triple bond over here. So let's take a look at that resonance form. So we'll go back to the beginning where we had this. And instead of putting the triple bond over here, now let's put it over here. Erase those two. We end up with something that looks like that. And now we calculate our formal charge, and it turns out the only thing is a minus on the sulfur. So what we can do is we can now add resonance arrows between these all. But the problem is that a really common thing that we're going to have to do is to assess the most prevalent resonance form, or what of the 3. We know it kind of looks like all of these 3 all at once. Which one of these is the most prevalent? Between these 2, it's a pretty easy decision, right? Because we have to minimize formal charge, and that's pretty classic. Also, by the way, one thing that we'll talk about as we get more practice here. Occasionally there'll be resonance forms where there are octets not satisfied. That's kind of like the first thing, that if you have some sort of resonance form that has an unsatisfied octet rule, usually that's going to be less likely than another one that has a full set of octets. That's kind of like the first level. The second level is minimizing that formal charge. I'll probably, assuming I can get to work, I'll scan in a resource guide that'll definitely help you guys out a little bit. So the point is, though, is that between these 2, it's a little bit more difficult to decide which one of those would rather have the minus charge. And that's where recognizing your electronegativities comes in. If you'll remember, there was a chart of like what atoms are the best at kind of holding on to excess electron density. And I'll probably put it as a text box somewhere, probably over my face. And it turns out that the negative formal charges would rather be on the more electronegative element if given a choice, right? And so I always wanted to name my first kid Fonkelburr. My wife said it wasn't okay, but, you know, just Audrey Fonkelburr, that's right. So Fonkelburr is really helpful mnemonic because it tells you the most electronegative elements in descending order. So fluorine is the most electronegative, and then usually when you're assessing your resonance forms, you just kind of look through the list and see, okay, is one of that representative? Yes, absolutely, right? I've got a nitrogen with a minus right there. So it turns out that, yes, this is a resonance form. We've got 3 valid Lewis structures here, but it turns out this one is most preferred. And again, don't fall into that trap that a lot of you know, on a lot of exams or organic questions, they try to get you to fall into the trap of saying, like, you know, which one would it rather exist as? Well, it wants to kind of exist as this, but it still has to be represented by these other ones, right? And it's truly not that, you know, there's a triple bond here sometimes, a double bond there sometimes, and a single bond there sometimes. It's all of those, all mixed together, but it's got the most double bond character is how you'd say that. That's what resonance is telling us. So in assessing resonance forms, just to kind of review, one is you pick the most prevalent resonance forms, or most preferred resonance forms. That's not easy for me to say right now. I'm sorry, it's been a long week. Are going to be the ones that have satisfied octets, right? That's kind of number one. Number two, you try to minimize formal charge. And number three is you try to put negative formal charges on the most electronegative atoms given a choice. And actually, the positive should go, if there is a positive, should go on the least electronegative element if given a choice. And there's a couple of other kind of more esoteric type resonance rules, but really that one will get you to the answer 99% of the time. Another really helpful concept that I'll just kind of take resonance as an opportunity to show here are reaction arrows, or technically these are not reactions, but you'll kind of get this, these arrow push problems all throughout second and third term, and it kind of leads to us being able to talk about mechanisms. So it turns out resonance is the first time where we can really start to use these arrows. And the point is, in organic chemistry, anytime you use an arrow, which, let's see if the red shows up okay. Yeah, that shows up okay. So anytime you see an arrow, right, that is a mechanistic arrow, you always go from a site of electron density, right, so minus charges, lone electron pairs or something like that, to a site of less electron density, right? And so it's always kind of a partially negative thing going to a partially positive thing, right? But the problem is that in terms of pushing arrows around, I just wanted to show you the proper way of doing things to convert between these resonance forms, because once you put the formal charges on there, sometimes you kind of screw things up a little bit. So what I'm going to show you in red here is going to be the arrow, technically a mechanistic arrow, or the arrow push that gets us from this form over to this form. So notice what I do is I go from a lone electron pair. I show that lone electron pair flopping down right here, right? So now if I stop there, I would have a triple bond. But the problem is that double bond now has to break. And it's going to swing up to that sulfur atom, right? And so that set of arrows, these mechanistic arrows right there, lead to a resonance form. And of course, we could do it the exact opposite way to end up with this resonance form. I won't show that because it's a little funky. Here we would actually have to go back to this before we went down to here. So I just wanted to kind of real quickly kind of sprinkle in a couple of things that we'll be doing a whole bunch of in the next couple of terms. So these arrows, just remember, really briefly go from electron density to less electron density, right? Okay, so the next couple of resonance questions are going to be just a little bit different than the ones we just saw. instead of having to come up with a Lewis structure, it's quite often something that you'll have to do to figure out if there are any other resonance forms for something. So to look at this, right, it turns out that there is actually another resonance form, and let me show you how like arrows can kind of help to get you there. So this is just one of the two resonance forms that this thing is going to be able to adopt, and the key is to recognize that you've got this thing called the carbocation that's out here, right? And also you have this double bond very, very close. This is something that we're going to encounter a whole bunch of times. This is called an allylic carbon, right? Because it's a carbon that is right next to a double bond. It turns out that this is a very, very, very common resonance situation that we'll find. And so I'm going to show you the arrow that gets us to the new resonance form. I always think about double bonds when they swing. They're kind of like a door. Right? And so this double bond just stayed connected to that center carbon there and just kind of moved itself over. And so what would result looks very similar. Except that it looks like that positive charge just kind of, that positive charge just moved over. Right? And so these are both what's called resonance hybrids of one another. And so you might say, what does this have to do with real life? Well, it turns out that if this thing is going to react, it just being able to show these two different resonance forms tells us where like this thing might react, right? If there is some sort of nucleophile or something that wants to attack a positive charge, right? So some negative thing, it turns out that just drawing this wouldn't allow us to recognize that, in fact, that carbon could get attacked just as easily as that carbon, right? And so it turns out that the overall picture of this thing, and again, these are pretty equally weighted, is that there's a partial positive charge on both of these carbons that is only told to us by the fact that we are allowed to do this other resonance form. And there's all kinds of different arguments that we're going to build into resonance eventually. Even the fact that you can draw a resonance form makes this thing much more energetically accessible. So we'll see a bunch of different examples where if we can draw resonance, those products are going to be much more likely, like an intermediate are going to be much more likely, and the products coming from them are going to be a lot more likely. So we're going to just kind of take a glance at another couple of examples of like how to do these kind of resonance forms. And in the next example, we're also going to kind of evaluate the most preferred resonance form as well. Here's another example of where resonance is really likely. Notice that it's very similar to the last one where we had some sort of charge that was exactly one atom away from something else with a double bond. Of course, this is a carbonyl, not an alkene like we saw before, but you'll notice that it's the exact same kind of thing. So what we could do is we could draw another resonance form where, remember, we're always going from a site of electron density, and we could do these two arrows to lead us to a new resonance form, which looks like this. And of course, we could do the two arrows. And so we'll just kind of go through. Maybe I should actually write the resonance rules down just over here. So first of all, satisfy octets. Things with satisfied octets. In other words, everything being satisfied means that it's a more prevalent resonance form. Minimize formal charge. Minimize formal charge. And then the third was negative on more electronegative element. And a few more that we'll learn. Okay, so let's kind of go through this list and just see if there's any difference here. Well, it looks like this guy and that guy have the same number of satisfied octets. By the way, if you wanted to, you could also draw the H that must be there too, because that carbon is only right now otherwise would be only seeing 6 electrons, which isn't very likely. Especially the fact that there's a negative formal charge there means that there must be a hydrogen there. And so number 1, right, between these two, they're the exact same. Go down to the next one. Minimize formal charge. Well, they both have a unit of minus formal charge in there. Negative charge on more electronegative element. Well, there the negative is on on a carbon. There the negative is on an oxygen. Think Funkelber, right? The second letter there is an oxygen. So it turns out that this thing would be more preferred as a resonance form. So more preferred. But, so it might not be a 50-50 kind of deal. It might be kind of a 30-70 or maybe even a 40-60. So most of the negative charge in this thing is situated out on the oxygen. Okay, let's try another one. This guy, you'll notice, first of all, a couple of things. We've got charges next to double bonds, right? That's classic resonance territory. And so what we're going to do is we're going to go and find the site of electron density. So I'm going to use one of these and see what kind of arrows I can push to end up with something. You notice that just flopped down there. So if I stop there, that carbon would be bonded 5 times, and we don't want that to happen. So I've got to break this bond. And let's just kind of do an intermediate here. And we'll show the products of this set of arrows. Which would look like that. So technically, this is a resonance form of that. But this thing where there's a positive and a negative really, really close, that's a classic kind of thing in resonance forms where you would say like, oh, that's not very likely. There are times where you kind of get stuck like that, but in this case, there's no reason that this guy can't flop down in between those, and what we end up with is this beautiful looking structure that looks like this. And there are my resonance arrows. So we're going to go through those rules, starting at the top. Are there any here where everything has a satisfied octet? Turns out yes. So right away, that thing is going to win just based on that assessment alone. The others, do we have minimized formal charge? That wins on that case too, because there is no formal charge in that particular one. And so this guy is without a doubt the most preferred. So this is most preferred. We'll just give this a number 1 here. We'll judge these other guys. So given the fact that these both have the carbon not seeing the full octet, let's use the second rule to judge this one and say, okay, do either one of these have any difference in terms of their formal charge, minimization of formal charge? And the answer is no. Okay, so let's go on to the third one. Where would we rather have the negative charge? Would we rather have it here, or would we rather have it on the more electronegative oxygen? Obviously, that guy is going to be the more likely choice. So in terms of judging this resonance, we could do something like this. And I could say you can go absolutely bonkers with resonance and start pushing arrows all over the place for like everything with multiple bonds and lone pairs of electrons. And so what I'll say is just kind of stay calm, and like as we keep practicing and we keep going through that like iterative give and take of you asking me questions and trying out a couple of things, you'll start to definitely pick up on kind of some of the patterns here. So that's probably a pretty good example. I think I'll do one more and then I'll finally let you guys get off of YouTube. Here's a good semi-trick question here. So let's go through a couple of different possible arrow pushes here. We keep in mind we always are looking for a site of electron density. Oh, I should probably put my lone pair of electrons up here just to not confuse anybody, so maybe you can even see it. And what we're going to do is we're going to recognize, well, there's a positive charge there, right? And so now this is going to kind of help us with our arrows a little bit. The fact that we see a positive charge kind of tells us that if we're going to show arrows, we better end with the head of the arrow pointing towards that positive charge. Okay, so that kind of gets us a start. Well, where could that have come from? It could have certainly come from there, right? So let's just do that. We'll draw the other resonance form down here, and we'll kind of do the complete picture and go through which ones we think are the most likely. Results of that arrow push with that red arrow right there would be this. Well, if doing it once is good, doing it twice is always better. Turns out we could have that arrow right there, and then I'll draw the results of that. And there is the result. So now let's go back and use our rules to decide which one of these is the most prevalent. You always start with that one where it says, regardless of anything else going on, where are all the octets satisfied? Is there anywhere where all the octets are satisfied? You'll notice here that carbon only is seeing 6 electrons in either one of these. So automatically this one is going to win the race. This is definitely going to be the most prevalent. And the dangerous thing about not recognizing that's the most important rule, that there will be times where I'll kind of lead you to kind of a trick question where, you know, there'll be like this positive charge on oxygen and you'll think, oh, that's really electronegative. It hates to have a positive charge. Well, yeah, if it has a choice, but it would much, much rather have, this compound would rather have fully satisfied octets. It can deal with the fact that there's a positive charge on a really electronegative element. So as I said, we're going to kind of develop some of these concepts here. This is getting some, this is going to be a little bit harder to answer between these two. Turns out that one is slightly more prevalent than that one for reasons I don't really want to get into, having to do with the donation of electron density through a bond. But the fact is that we've learned a lot actually today, and a lot of things that we're going to keep talking about and keep developing our skills with. We have, let's see, what did we talk about? We learned about doing Lewis structures, more of kind of a gen chem kind of thing. We learned about resonance structures. We learned some rules for how to determine which resonance structures are the most prevalent. And we also started to learn these arrow pushes. We kind of saw these things which we're going to eventually term mechanistic arrows. So there's a lot going on there. So I think we're going to kind of keep today pretty simple. I would really like you guys to kind of engage a little bit with the homework before you get into the weekend. And please ask me some questions in today's office hour. All right, bye-bye.